Welcome, dear students, for the next class. And in this last class, we discussed the definition of a normal subgroup, and then we prove a result that uh, every subgroup of an abelian group is normal. And then in the end, we have to provide an example that the converse of that theorem is not true. Means we have an example. We show that non-abelian group, but all the non-trivial subgroup of this quaternion groups are always normal. So now this lecture we start one more example. In the group we have to discuss that the every 2 by 2 invertible matrices form a group under the matrix multiplications, and then we have to take a special linear group SL2, and then we have to SL2 is clearly is a subgroup of a G. So now we have to try to find out, is this SL2 over the elements of a R, all the 2 by 2 matrices with the determinant of 1 is a normal or not. So we have to try this because SL2R is clearly, if we take all the element of a G where determinant of a is not equal to 0, and in this case all the elements of A and B where determinant is equal to 1. So we have to show that if we have to multiply it by the left side and the right side, and then we have to just say that left cosets and the right cosets of this N and G are coincide. So we just say that A is the element of a GL2 and B is the element of a SL2. By the basic property of a determinant, we compute, we have to just show that this is B inverse. So we have A inverse. So this means we have to just say that by determinant of A inverse, and A inverse can be written in the form of a determinant of A, determinant of a B, determinant of A inverse, determinant of A, determinant of a B, because B belongs to the SL2. So determinant of a B we have a clearly is equal to 1, and then determinant of A into determinant of A inverse. Then by the property of this determinant again, determinant of A into A inverse, determinant of A into A inverse, because we have to take in the I2. So determinant of I2 is always 1. So this means we can show that, so this means A inverse is the element of a N. N means we have a SL2. So we have to just say that that B is equal to the SL2. This means B is the element of N. So we simply say that is the element of N. So this implies that we can say that we have a N, A inverse, we have a containing into the N, and then we have to show that AN is equal to same as a confirming this. This is SL2 R is a normal into GL2R. So this means a special linear group is a subgroup, and that is a normal subgroup of a group, general linear group of an element. So now we have to prove the next result, where we just N is a normal subgroup of a G. If index of a G is equal to G and NR is equal to 2, then N is always normal in G. So we say that if we have any subgroup of this, we calculate the index of this with the G, and if the index is equal to 2, then we know that this means we have a abelian. This is every group of, and then this no N is always is a normal into G. So let we have to try, given the G and index of a G and R is equal to 2. So we know that N has a 2 left cosets. If index is equal to 2, so this means index is equal to 2 means G has a 2 left cosets, and one of the left coset is itself. So there is a simply we can say that N has a 2 left and 2 right cosets. And one coset is N is always N, because N into E is always one of the coset. So this means clearly N is the one of the coset. Then we have to another coset we have to. So this means if in index of this is this means exactly 2 cosets are there. If it's 2 cosets are there, 2 left or 2 right cosets are there, and then one of the coset is clearly we have always is N into itself, because we have to the N is E is equal to you have a N. So 1 is the coset is equal to we have a, whenever we take a identity composition of this with the identity n giving itself. This is the one of the coset. So this means n is itself one of the coset. Now we just say that let g is not equal to n. We have to take g which is not belongs to the n, and then gn is the another left coset, and ng is the other right coset. So we take, if n is the one of the set, then g we have to choosing the element which is not the member of n but is there some element of a g. So g is not an element, then gn is the other left coset and ng is the other right coset. So we have n union, you know that all the we have a result, this union of the all the coset is giving the g. So this means either right or left. So n union n union gn is equal to g, and also you have a n union ng is equal to g. So this means we can say that n union gn is the same as n union ng. If we have a these two are the same, we have a n union gn is the same as a n union ng. These since these are disjoint union, so it follows that the union is a disjoint. This only possibility is what? This means gn is equal to ng, and therefore we can say that g and g inverse is equal to n. So we can say that this equation holds for any g in the coset of a gn, and this equation clearly holds for any element of the trivial coset n. Hence the equation holds for all elements of a g, confirming that n is a normal subgroup of a g. So this equation holds for any g in the coset of gn. That means this is then this equation clearly for any element of a non-trivial coset. Hence the equation holds for all the elements of a g, and confirming that this n is a normal subgroup of this group g. If a index is equal to 2, then we can simply say that we have this as a normal subgroup. So for example, you have a A4, we have a an is the we can take simply the A4 is a S4. This is an. An is a normal subgroup of Sn, where an is the alternating group. Now you know that that is the index of Sn, and an is the same as a size of a Sn over size of a an, and then this is the size of Sn is equal to factorial n, and then size of this is factorial n by 2, and then this is equal to 2. So this is means clearly we have to just say that index of this Sn with an is equal to 2. So if index is equal to 2, then by the previous theorem we can simply say that an is a normal of Sn. So an clearly is a alternating group, is a subgroup of a G, and then index of these two are 2, and similarly we can say that this an is a normal subgroup of the group of permutation of n symbols Sn. So this is the by the using the previous theorem we can simply say that every an is a normal to Sn. So now we have to move to the another interesting result. Let G be a group and as a normal subgroup, and K is also normal subgroup of a G. We take a two normal subgroup of a G, then we show that intersection of these two normal subgroup N and K is identity, then Nk is equal to Kn for all Nk is equal to this thing. So we can say that simply is equal to N and K are two normal subgroups. If N and K are two normal subgroups, then we have to show that the intersection of these two normal subgroups is nothing but is equal to only identity element. If this is the identity element, this means we can simply say that Nk and K are the, if intersection is identity, then we can simply say that Nk is the same as a Kn for all n belongs to the n and K belongs to the K. Consider we have to write Nk, n inverse, K inverse, we have just denoted as a alpha, and then we have to writing in this form this n, K, n inverse, K inverse, and if writing to this form we have, since n is a normal in G, then we have to, if it's normal in DG, means we have a this element K n inverse K inverse this is the element of a k n and k inverse, and this is equal to nothing but is equal to n. So by the normality, if this is the normal for all k is the element of a k, then this k n inverse if k is the element of a k, then k inverse is also the element of a k, and n is the element of a n is the element of n, then n inverse is also the element of n, and this means this is n is a normal in G. So this means we can say that simply we write into the this form. So and k is a subgroup of a G. So this means clearly we have to say this is equal to is the element of this is nothing but is equal to n by the definition of a normality. And then if this whole thing belongs to the then k and k inverse and k inverse is the element of a k, hence alpha is equal to this, and this is the already n. So this means this alpha is equal to this whole thing is the element of a n. If this whole thing is the element of a n, then we have to simply write similarly alpha can be written in the form of a we write as a n inverse k n inverse, and if k is a normal, then this is the element of a simply is equal to k, and then we have this is the element of a k, then this is equal to as the element of a pura whole is equal to k. So because k is a normal in G, the similar for the above we can just write this k is also written in the form of this alpha can also written in the form of this n inverse k n inverse and then k inverse, and that is the element of a k. So we can say that alpha is equal to is the element of a n, and this alpha is the element of a k. That means alpha is the element of a n intersection k, but n intersection k is given the identity. So this means alpha is equal to you have an identity. If alpha is equal to identity means you have n k n inverse, and k inverse is equal to you have a identity, and then you have a, if this identity, then you can say that n k you have a n inverse and k inverse is equal to identity means we simply say that nk is equal to you have a k, and then we have to prove that for all n and k are the element of a n is the element of a and k is the element of a. We can say this is simply we have to just say that nk is equal to nk n inverse. So we have nk n inverse k inverse is equal to identity. We can write nk n inverse, we have a k inverse k is equal to ek, and then you have n k n inverse is equal to k, then again n k n inverse n is equal to k n, and then we have to show that n k is equal to k of n. So this complete the proof of the theorem. We have to show that two types of some elephant alpha we have to denote in n k n inverse k inverse, and then we show that this is the element of a n, and the same element is the element of a k, and then actually this is come into the mind because we have to show that nk is equal to kn, and then we have to write into this form, because if you take we take inverse of this, we writing in the inverse of this, you can write n inverse k n inverse we have to multiply it. So this alpha can be also written in the writing the same way. We have to show that this alpha is the element of identity, then alpha intersection is identity, then we can say that sorry, this can be written nk inverse, sorry, this is nk n inverse and k inverse, not inverse. Okay, this is not the inverse. This is alpha can be written as nk n inverse k inverse, and this is the element of a this is the element of a k, because k is a normal. So this means we can say that alpha can be written in the form of a identity, and by this identity we can say that this is, so this is the same alpha, not the change alpha we have. This is by mistake is putting identity inverse is element is inverse is into here. So this completes the proof of this theorem. Now we have a definition. Let n be a subgroup of a G. For any G, we write G inverse Ng is equal to Gn G, where all n is the element of n. So for any G belongs to G, G inverse G Ng can be written in the form of G inverse Ng, and then we have to show that if n is a normal subgroup of a G belongs to the G, then G inverse Ng is a subgroup of a G, and then we have to show that the order of a G inverse Ng is the same as a order of this subgroup. So first we show that this element G inverse Ng is equal to for non-empty, and then we have to show that this is closed under this operation, and then every element inverse is also belongs to that set. So we take simply into this form. So if we take identity is the element of clearly is this set, so we have to show that clearly this set is a not non-empty because E is the element of n, and then E can be written as a G inverse E of G, and then this is nothing but is equal to G inverse N G. So this can be written in the shape clearly, and then this identity is the element of a G inverse N G, and that is clearly this is not a empty, right. So we have a clearly this is non-empty set. Now we have to show that take two different elements of G1 G inverse N1 G and G inverse N2 are the element of a G. Then we show that the composition of this, we have a G inverse N1 G and then G inverse N2 G, and this can be written as a by the associativity condition we can write G inverse G inverse N1 and then is equal to G and G inverse N2 and G, and this can be written as a G inverse N1 identity, N2 is equal to G. This can be written as a G inverse N1 N2 G, where N1 is the element of N and N2 is also the element of N, and because N is a subgroup of a G, so N1 N2 are the element of N. So this whole thing is the element of N. So this means this G inverse belongs to the G inverse G, and then we have to taking the two different elements G inverse N1 G and G inverse N2 G belongs to this set G inverse Ng, and then finally we show that the composition of this this product of these two is also belongs to the G inverse Ng. That means this is a closed under the whatever operation we have. So we can simply say that the product of these two is also belongs to the Gn. So one of the condition we have to show that identity belongs to this set, means this set is a non-empty and is also closed. Since n is equal to n1 n2 this thing. Now we have to show that the inverse. So finally we have to, if this is the element of a Ng, now we take a G inverse and G, so we take the inverse of this, so we take a inverse of this, and this can be inverse of this can be written as a G inverse. Now we have a N inverse, we have now we have it written as a G inverse to inverse, and now this is nothing but is equal to G inverse N inverse and G, and N is the element of N, then N inverse is also the element of N. So this means this whole thing is belongs to the G inverse N of G. This means this element is the element of this, and now if you see if we take a composition of this is giving the identity element, this means if element of this is the element of a G, the inverse of this also belongs to the same set. So this means they satisfy all the properties of a subgroup. So this means clearly we have to share that G inverse and G is a subgroup of this G. Okay, so this means this is a subgroup of a G. We can simply say that. Now we have to show that by the definition G and G, it is clear that we can only one element of each element of n, but G inverse N1G is the same as G inverse N2G. So we have to just write now N1 is equal to by the cancellation property we can say that n1 is equal to n2, and this means if n1 is equal to n2, so this means the size we have all the elements of a this the same, so order of G inverse n is the same as the order of order of n. So G inverse ng order of this is the same as the order of the our subgroup. So we can simply prove that means if we have a G and G inverse is subgroup, and the size if n is a subgroup, then G and G inverse is also is a subgroup, and this the size of this is the same as a size of a n we have. Now in the following theorem we give some condition n is a subgroup is equivalent to normality. Now we have to next theorem is giving the some conditions, so we have to this some conditions we have to prove that is under certain conditions are equivalent for the normality. So let G be a group and n be a subgroup of a G, then the following statements are equivalent. N is normal in G for all G inverse G and G containing n, for all G and G inverse is equal to n, and for all G n is equal to ng. So this we can say that these are the four equivalent conditions. If we have a n is a normal, then this hold conditions, then we have to just say that A implies B, B implies C, C implies D, and we have to show that D also implies A. So this means all are the equivalent, and then if we equivalent, then we have to, if we have to just say that if G inverse ng is equal to n, then n is a normal in G, or G inverse ng containing in n, then we can say that n is a normal in G. So these all are condition is equal. Now one by one we have to try to prove this. First we have to show that n is a normal, then G inverse ng is containing into the n. So if one implies B, since n is a normal, so this means we have, if n is a normal, then clearly you have to say that for G is equal to G of n. Means right coset and left cosets are the same, so coincide. So we can say that if n is a normal, so G and G inverse is equal to containing into the n for all into G. Now replacing we have to just say that like this, we have to like this, so we have to simply say that we have a Gn G inverse, so we have to say that Gn is equal to n of G. This can be written as G of G inverse is equal to, we have a is equal to n. So this means we by this property we can say that G of n G of n G inverse containing into n. Now we replace, because G is the element of a G, so we write G inverse is also the element of a G. So this means write in place of a G we write a G inverse n, G inverse ka inverse is also containing into the n, then G inverse n, and G is containing into the n. That means if n is a normal, then by the definition we can say that left coset and right coset are coincide by this G and G inverse coincide containing to the n, and then G inverse this is equal to we have to just say that. So from this B is hold. Now next we have to show that if B implies C, so B implies C means we have to one way is very true, we have to just say that let G is the element of this. Since G and G inverse containing n, we only to show that n containing G and G inverse I just take G and G inverse. So we have to just say that. So we just take a, in the form of this if n is this is okay. So we have to just take G and G inverse is containing into the n. So we need only to show that n containing into the G and G inverse. For n is the element of n, then G inverse we have a G inverse ng can be written as a G inverse and G inverse ka inverse, and that is the element of a n, and this is the element of a because G and G inverse G is the element of a this. So we can write in the form of a, this can be G inverse and G is equal to is some n, and then some n prime is the element of n. So we can say simply that therefore this n can be written as a Gn Gn prime G inverse, and Gn prime is Gn and G inverse. So this means we can say that this is n is the element we have to taking the from n, and then we have to show that n is the element of this. This means n is containing into the Gn G inverse, and Gn G inverse is already containing the n. So by these two we can say that n is Gn G inverse is equal to n, and then we have to say that Gn is equal to Ng. So if these two hold, then we can say that now C implies A. We have to just say that suppose this G and G inverse is equal to n for all G, then for on there exists some n prime n such that G and G inverse is equal to some n prime. This is the element of a n, and consequently Gn is equal to n times G, or we can say that Gn containing into the Ng. Similarly, we can say that Ng containing into the Gn prime. Then by these two we can simply say that then we have to this thing. Now this is the C to D. Now we have a C prime C to D. Same we have a this thing, and then we have a Gn G and G inverse is equal to n for all n belongs to the n. For giving G belongs to G, n belongs to the n, there exists n prime. Then we have a n is equal to this. So G is equal to this. Then Gn containing into the Ng, and then similarly we have to proving this. This proves that Gn is equal to Ng, and then we have finally is equal to D implies A. For any G belongs to G, n belongs to the n, Gn belongs to the Gn, and Gn is the same as Ng. So Gn is the element of Ng, and Gn is equal to n prime G, and some n prime is equal to this. This implies that if Gn G inverse is equal to n prime, and this is equal to n, and then this means can say that if G and G inverse is equal to n, then n is a normal subgroup into this form. So we have to show that this means clearly we have show that clearly we have a we have to just say that A implies B, A implies C, A implies D, B implies C, B implies D. So we have to satisfy this all the result of this. This means A implies B means we have a normal subgroup. Then we have to show that if A is a normal, then this is contained into this form. And then second one we have to just say that A implies B if n is B is implies C. If this containing, then this is the same as equal to n. And now we have to show that C implies this is a D. If we have a Gn is equal to n, then we have to solving this form, and then finally this just repeating this form. So this is the okay. This slide is repeated. So C implies D is we have to prove, and then we have to finally we have to prove the D implies A also. So D implies A also. This means we have all this equation hold for all the in this way we can say that this true for each and every set. So A implies B. This is the equivalent condition. If n is a normal subgroup, then this B, C, D are equivalent. We can say that. So we have to using now we have this example. Let G is equal to S4. That the elements of S4 are this form. Now we take n is a one subgroup of this. We have this element of E 1 2 3 4 1 2 and 3 4, and then the question is this is n is a normal to S4 or not. So if n is a normal to S4 means this all the elements of this S4 this elements is satisfy the condition of left coset and right cosets are coincide. So just we comparing the right and left cosets of n in S4, we say that 1, 3 and 2, 4 clearly we have a 1, 3, 1, 3 and 2, 4. I take this element from here, and then we have to try to 1, 3, 2, 4 n is equal to, we have a this types identity case, this is itself. Then we have in this, now if we go to the right side, 1, 3, 2, 4, now we have 1, 3, 2, 4, 1, 4, 1, 4, 2, 3, and then we have this. Now this is we have to show that these two sets are the same, but this of course not enough to conclude that this n is a normal to S4. So this is not enough. We have to show that n is a normal to S4, because we have to show that for each and every pair of a G coincide with n is a left and right cosets of this are the same. So we take some another element. For example, we take a 1, 3 is also the n. So 1, 3 n we taking in the form of a this is coming into this form 1, 3, 1, 2, 3, 1, 3, but we have to read taking n 1, 3, then is equal 1, 3, 1, 3, 2, and then this is, now clearly you see these two are not the same. So we can say simply that we have a 1, 3 n, and these two are set different. So 1, 3 n and n 1, 3 is not the left cosets and the right cosets are not coincide. So this means we can simply say that whatever set n we have to taking in this example is not a normal subgroup for this S4. So this means we can concluding here this is clearly is not a normal subgroup. Now if suppose we have to change n into this form, I take again the SG is equal to S4, and I take a subgroup into this form, n is equal to E 1, 2, 1, 3, 2, 3, 1, 2, 3, and 1, 3, 2. Now again the question is this n is a normal into S4 or not. Now in this case you can see I use the property of a G and G inverse, and then by this property of the theorem we say that if n is a normal, then G and G inverse is also equal to n, and then if we have to try this, we take a 1, 4 for this n, and then 1, 4 inverse, then 1, 4 and 1, 4 inverse of a 1, 4 is equal to itself 1, 4. Now if we multiplied this, you getting this element, and then this is clearly is not equal to n. So this is again we can say that this n is not n normal into the S4. By the theorem we can simply say that no need of calculating the left coset and the right coset. We simply say that if we take any choose element of a G, and then if we take n and then inverse of this if you take another element, suppose 1 of the element of a G, 1, 2 and 1, 2 inverse, and then similarly all other elements. So if you show that if this is the same as n, if coming into the n, then if true for all the G, for all G belongs to G, this is hold, then we can say that n is a normal subgroup, otherwise n is not a normal subgroup. So now I just I have to discuss this normality of a subgroup, and then we have to simply discuss some examples, interesting example for S4, and then we show that, and then show that this is two methods for S4. I take this is a normal subgroup or not, and then this is again we have to taking the some different examples here. N is equal to, we take a different subgroup of this, then from this I have to check one of the cosets coincide, but we have to take another coset is not coincide, that means it's not a normal subgroup. Then for the same group I take a different subgroup, and then this way we have to try to find the solution by using the theorem. The theorem says that if G and G inverse also is equal to n, G and G inverse, if G and G inverse is equal to n, then n is a normal. for all G belongs to G. So I take one of the element here 1 4 and take a inverse of this and then simplify this, then this is not satisfied, this is not equal to n. So this means clearly this again this subgroup is also is not an normal into this. So now I have to stop today's lecture here, and then I will continue the some more properties of a normal subgroup, and then we have to go for the quotient group later on. So now thank you very much.